We are currently building artificial minds capable of synthesizing human knowledge, but they are entirely trapped inside a very physical, finite glass box, GPU memory. The primary culprit taking up all this space is the key value cache. You can think of this as the AI's high-speed digital cheat sheet. It's where the model temporarily stores the context of your prompt, so it doesn't have to constantly reread what you just asked. Here's the problem scaling that up. When you ask a model to read an entire codebase or a massive textbook, this digital cheat sheet swells exponentially. It rapidly eats up available GPU memory, and when that bar hits 100%, the system crashes. The roadblock preventing us from feeding AI even larger datasets isn't a lack of computing power. We simply do not have the physical space to store the model's active thoughts. The standard industry fix for this is vector quantization. This is a compression technique that mathematically shrinks these massive, high-dimensional arrays of numbers down so they actually fit inside the cache. But standard quantization comes with a fatal flaw: memory overhead. To remember how to unpack compressed blocks later, the system must attach bulky decoding instructions to every single block. These instructions take up so much room they defeat the purpose of shrinking the data. Researchers at Google have developed a solution called TurboQuant. It is a compression framework that crushes the key value cache down to just 3 bits per value, while completely eliminating this memory overhead. Achieving this requires a 2-step mathematical redesign of how an artificial neural network geometrically maps meaning. The first step of this redesign is an algorithm called Polar Quant, and it works by changing the geometry of the data before compression even begins. Natively, AI memory plots data on a rigid Cartesian grid. To locate a concept, the system has to trace strict right-angle paths along the x, y, and z axes. For high-dimensional data, this is highly inefficient. As new vector points appear, the outer boundaries of the data constantly shift and warp. The model has to generate and store those bulky metadata instructions just to keep track of where the borders went. Polar Quant solves this by abandoning the square grid entirely and converting the data into polar coordinates. Now, a concept's location is defined by a single straight line from the center, its radius or strength, and a sweeping arc that indicates its angle or direction. Because the pattern of these angles maps onto a highly predictable circular grid, the model automatically knows where the boundaries are. It no longer needs to store those bulky decoding instructions, and the memory overhead dissolves away entirely. By translating the data from a shifting box to a stained circle, Polar Quant achieves massive compression without carrying the traditional memory baggage. There is a slight catch. This aggressive geometric rotation simplifies the data beautifully, but it leaves behind a microscopic layer of mathematical error and hidden bias. To clean this up, TurboQuant employs a second step called quantized Johnson-Lindenstrass, or QJL. This acts as a precision finisher to correct the leftover bias without adding any new weight to the data. You can picture QJL as an intense 1-bit laser. It passes over the compressed data and violently shaves off those microscopic imperfections, snapping the complex values into a strict binary state of either +1 or -1. The key property of QJL is that even though the data is reduced to pure binary shorthand, the relative distances and structural relationships between the data points remain perfectly intact. QJL acts as the essential counterbalance to Polar Quant. Together, they ensure the AI retains a flawless understanding of its context, even when its memory is brutally simplified. When you take this microscopic mathematical efficiency and apply it to physical hardware, like an NVIDIA H100 GPU, the macro effects are massive. The TurboQuant framework successfully crushes the key value cache down to just 3 bits per value, and it does this entirely post-training, requiring absolutely no fine-tuning of the model itself. This chart shows exactly what happens to the hardware. The key value memory footprint plummets downward by a factor of 6, yet the secondary line showing retrieval accuracy on complex needle-in-a-haystack tasks, tests designed to see if an AI can find one tiny fact buried in massive texts, remains perfectly flat at 100%. Because the data is now so incredibly light, the H100 chip can calculate attention scores, the specific process an AI uses to decide which parts of your prompt are important, up to 8 times faster than it could with an unquantized model.
These benchmarks prove that the memory wall blocking AI scaling can be demolished through software elegance, bypassing physical hardware limits entirely. For the end user, this six-fold reduction in memory directly expands the context window, allowing models to process thousands of additional pages of text on the same hardware. It unlocks the ability to run instant semantic vector searches across billions of documents simultaneously. The industry default has been to assume that building omniscient AI requires infinitely larger, hotter, and more expensive server farms. TurboQuant proves we can achieve the same goal by rethinking how an artificial mind maps meaning. So, what do you think? Does the true path to artificial general intelligence lie in pouring billions into massive physical hardware infrastructure, or in brilliant mathematical optimization like this? Let me know in the comments.